Hello, students. Welcome to another edition of Physics with FOM. I'm your host, FOM, and this is the day 4 lesson. This should be today's date is April 2nd, I think. Yeah, April 2nd, 2020. What I wanted to do today was work Newton's law of gravitation with you. So it's going to take roughly around 10 minutes. I'm going to work a couple examples, go over how affecting one thing affects the overall force of the other, and then you're going to get some practice problems to do. So in front of you, right down there or up there, I don't know which way that is, you should see Newton's law of gravitation. Remember, there's one number on here that you will always know, and that's the gravitational constant. So I'm going to go ahead and just draw it on here. Why did you not draw? All right, G, you will always know that, and it is 6.67 times 10 to the minus 11. Now, minus 11, that's going to be multiplied times these masses. You would see that it would really create a very, very small force. So if you're looking at objects like two apples, which are going to have small masses to begin with, because if you look at the gravitational constant, you look at the unit for that, you have newtons times meters squared over kilograms squared. You would see that we need to work things in kilograms, so bigger masses than an apple. But you multiply that gravitational constant, it's going to reduce everything down. So we definitely need to have bigger objects to work with. What is this? Oh, it's a string on my neck. Okay. So you're always going to have G. I'm going to have to tell you masses. I'm going to tell you distances. Notice that the distances again are in meters. So if I give something to you in kilometers, you're going to have to change that into meters. If I give you something in grams, you would have to change that into kilograms. So there's our equation. We're going to write this down. G again, as usual, 6.67 times 10 to the minus 11. All right, so we're going to look at large bodies. They have to be large bodies. So let's look at two asteroids sitting in space. And asteroid 1 has a mass. Now, my masses have to be in kilograms again. So let's say that this object has a mass of uh, 600 kilograms. All right. It's next. When I say next, I mean it's in the vicinity of another object which has a mass of 100 kilograms. So one object obviously is more massive than the other. And I know that they are in meters. Let's say they are 10,000 kilometers away from each other. So their distance is 10,000 meters. I said kilometers. They're 10 kilometers away from each other, but they are 10,000 meters from each other. So now I have all these numbers. I can figure out what the gravitational force between them is. So I would do F grav is equal to my constant, which is 6.67 times 10 to the minus 11. I'm going to multiply that times 600 kilograms times, I'm running out of space here. This is kind of difficult. 100 kilograms. There we go. This is going to be super sloppy. And that's all going to be over 10,000 meters squared. So I have 10,000 meters squared. I'm doing this like Khan Academy. All right, so I'm going to type all of that information into my calculator. That's a lot of information. Let's see, let's bring up my calculator app. This is the first time I've used my calculator app. This is not it's the wrong one. All right, where are you at, calculator app? By the way, I'm also conveniently killing time as well. No, that's not it. Where are you at? This is ridiculous. Can't find my calculator. Doop, doop, doo. So awkward. Anyone see my calculator app? No, you can't. All right, well, I'm going to pause this. All right, I'm back. I now have a calculator handy. So we're going to enter this part one at a time, starting with our gravitational constant, which is 6.67. Hit the EE button if you have it. Hit the negative sign, 11. We're going to multiply that times our asteroid's mass of 600 kilograms times 100 kilograms. That's the mass of asteroid 2. We're going to divide that by our distance squared. So I'm going to type in parentheses our distance squared. Well, it's 10,000 meters. It's a pretty big distance. And then I'm going to square that. And then I'm going to close parentheses. And then, oh, Twitter got some notifications. Get off of there. There it is. That is, wow. It's not a lot of gravity. So if I was going to put that into scientific notation, that would be 4 times 10 to the 3, 6, 9, 3, 6, 9, 12, 13, 14, minus 14 newtons. So I essentially have these two, fairly big objects, 600 kilograms. That's the size of a small car. And then the 100 kilogram one, maybe like a washing machine, and they are really, really far apart, 10,000 meters. They exert a force of, very, very small gravitational force. So you can see what happens because of that gravitational constant. It greatly reduces the size of my force, especially if my objects are far away. So let's do something different then. Let's take two objects these same objects, and let's put them really, really close together. So I'm going to go back and then, okay, get off of here, whatever you are. All right, I'm able to draw. Yeah, there we go. So I'm going to take these same objects. I have mass 1 is going to be 600 kilograms again. Mass 2 is going to be 100 kilograms. My gravitational constant still 6.67 times 10 to the minus 11, but let's make these objects really, really close together. Let's put them 1 meter close to each other. So my distance is now just 1 meter. So to figure out the force of gravity between them, I'm learning I need more space. I'm going to take 6.67. Ooh, that's awful. Let's fix that again. You know what? I think I'm going to try this handy dandy pen I've got. Which is going to require me to move this down. I don't know if I can do this because I'm going to have to float. Let's see. Oh, nope, nope. It's going to write again. All right. We're going to do 6.67 times 10 to the minus 11. Pen, not that great. Not working out. There we go. This is fun. We're going to multiply that times our mass, which is 600 kilograms, times 100 kilograms. And that's all going to be over 1 squared. And we should all know by now that 1 squared is simply 1. So I'm going to take my numbers. I have 6.67 there, minus 11. Going to multiply that times 600 times 100, and there we go. So our new force is now 3, 6. It's roughly 4. Our force of gravity is 4 times 10 to the minus 6 newtons. So these are, you could say these are fairly common day objects. A car and a washing machine, small car, washing machine. You put them together, and they're going to exert a force of less than 1 newton on each other. So obviously, they are not going to overcome gravity on Earth. They're definitely not going to move towards each other. You put two people, sit them down right next to each other, and if they can be absolutely still, the gravity between them is going to be really low. So much so that they are not going to be attracted to each other unless they are attracted to each other. So I think on the previous problem, the gravitational field, the force of gravity was like 4 times 10 to the minus 11. So very, very small. So to get appreciable forces between these objects, they have to be so much bigger. So let's kick it up. Let's go 2 objects. First object has a mass of, let's say, 3 billion kilograms. That's awful. I got to use my pen. And then mass 2, let's say it's got a mass, or let's go 10 billion. Awful. Let's put them at a distance of 1 meter again. So now distance is 1 meter. So F gravity then between the objects is going to be our gravitational constant, 6.67 times 10 to the minus 11. And then now I'm going to have these big numbers. So it's 3 times 10. That's going to be to the 369 to the 9th kilograms times 1.0, or just 1. Let's erase that. 10 billion is going to be, let's see, 369, yeah, 10. 1 times 10 to the 10th power kilograms. So far more massive objects. These are mountains. These are huge objects. Let's see what happens to the force. Automatically, I can see with this exponent and that exponent, if you follow the law of exponents, when you multiply things, you're going to add those exponents. So already I'm sitting at something that's going to be times 10 to the 19th power times this force over here. All right, so let's see what happens. That's all going to be over 1 squared. Get off of there, not now. I'm not going to rate you. All right, so let's type in our numbers. 6.67 EE to the minus 11th. We're going to multiply that times 3 EE to the 9th power. That should be 3 billion. Got to do the little jumps here, here, here. Yeah, that's right. And then multiply that times, oh, now my number's a little bit bigger already. I'm going to multiply that times 1 EE to the 10th power. And let's see what happens to the force of gravity between them. Now we're talking. That is some appreciable gravity between these two objects. That is a gravitational force of 2 billion newtons between them. So you got really, really, really large objects that are 1 meter away from each other. And that's center to center. So these are super dense objects. If the distance between them is just 1 meter, that's extremely dense objects, a lot of matter pushed into a tiny place. You have a force of 2 billion newtons. So that is how you work Newton's law of gravitation. Your next assignment is going to be on the same sheet of paper as everything else, where I will give you all the numbers, and then you're going to enter the information, your answers, into that Google Sheet, into one big sheet for this entire week. So if you have any questions whatsoever about how this is done, please let me know. I will be available, and there's all kinds of calculators that you can use online, and then you can just re-watch this video to see how this problem is worked out. But I will talk to you tomorrow, and have a good day.